So, welcome to Eiji, and would you like to start talking now?
Oh, yeah.
I think you're allowed to share the screen if you want.
Yes, I want to share screen. Oh, can I start now?
Yeah, sure. Yeah.
Okay.
Start
Yeah.
now. Yeah, that's fine.
Yes. Thank you very much. Uh, I'm glad to talk here. Yeah.
Yeah, no
Today's
problem.
today's title is quantum invariance of length and three manifolds with boundary defined via virtual links. My name is Eiji Ogasa. This talk is based on the joint work of Kaufman and me. Uh, Abstract, we use virtual links and introduce new topological quantum invariants of compact-oriented three-manifold with boundary, where the boundary is a disjoint union of two identical surfaces. These invariants are now new, non-trivial, and calculable. By using our new invariants, we give a new invariant of classical knots and rings in the three sphere. Virtual ring invariants make new classical knot and ring invariants. Today's contents, Section 1, quantum invariants of three manifolds. Section 2, quantum invariants of classical knots and rings. Quantum invariants of three manifolds with boundary defined via virtual links. Take a link in a second surface. Second torus includes a link. As you know, we can regard links in second surfaces as virtual links. By using linking number of virtual links, we can introduce a framing for each component of a link in a second surface. We can also define the linking number of two components of a link in a second surface. Note, we cannot define a linking number of two component links or a framing of a knot in compact-oriented three manifolds in general. Let F be a closed-oriented surface. A framed link in a second surface represents a connected compact-oriented three manifold M with boundary, whose boundary is F and minus F. It also represents a compact-oriented four manifold X such that, it V. V equal second surface cross interval and four-dimensional two handles. Here we attach four-dimensional two handles to second surface cross plus one. conceptual figure. Second surface cross interval and attach four-dimensional two handles. So frame to link in a second surface represent three manifold and four manifold. We obtain a framed virtual link from a framed link in a second surface. A framed virtual link is a virtual link, each of whose component is equipped with a framing, like that. Note, a given virtual framed link represents many compact-oriented three manifolds because there are infinitely many possibilities of the homeomorphism types of boundaries. If we are given a framed link in a second surface, we can make one framed virtual link, but from a framed virtual link, we may get many second surfaces with framed link. Let F be a cross-oriented surface, maybe connected. Let M be a connected compact-oriented three manifold with boundary, whose boundary is F and F. Or remark, for an oriented manifold X, we sometimes write minus X as X when it is clear from the context. Due to Morse, Milner, Smell, Kirby, Fan, Rook, Licorice, etc., we have the following. M is represented by a framed link in F cross the interval. Let M be a connected compact-oriented three manifold with boundary. The boundary is Z and H. G and minus H are orientation preserving default to a cross-oriented surface F with Venus G. Fix a symplectic basis, standard basis M1G, then MGG, M1H, the MGH, L1G, the LGH, L1H, the LGH for Z or H. The standard symplectic basis there. Under these conditions, the three manifold M is said to satisfy the boundary condition B. We shall define topological quantum invariants of three manifolds M with the boundary condition B. Define F cross the interval with the symplectic basis condition F as follows. Take second surface, fix a symplectic basis M1F, the MGF, L1F, LGF for F as usual. Fix basis cross plus one, basis cross plus one, minus one in both sides. Roberts generalized Kirby's result and Fan and Rook's result and proved the theorem which is stronger than theorem 1.4. This theorem follows from Roberts' result. F be a closed-oriented surface, M be a compact-oriented three-manifold with boundary, whose boundary is F and F, with the boundary condition B. Let L0 and L1 be framed links in second surface with the symplectic basis condition F, which represent M. Then L0 and L1 are related by the moves O1, I show now, O2, O3, and frame the isotopy in F cross minus 1, 1. These are Roberts' moves. Oh, I'm sorry. I'll be back soon. These are Roberts' moves. +1 and -1, blow up and down. It is a handle sliding. This is extra move. In the case of the three sphere, we only use these two. But Roberts discussed general three manifold. We need this move. Roberts discussed a little more general case, but today we need this case. F be a closed-oriented surface, M be a compact-oriented three manifold with boundary, whose boundary is surface and surface with the boundary condition B. L0 and L1 be framed links in second surface with the symplectic basis condition F, which represent M. Then L0 and L1 are related by the moves O1, O2, and O3. We need the O3 move definitely. Look at figure 1.8. Kirby draw it, Fan, Rook draw it too. In the right figure of figure 1.8, this figure, we draw a framed link in the second, in the torus. It's a solid torus. This is a solid torus, not the second torus. It's a second torus. By Roberts or Kirby or Fan Rook theorem results, they represent the same three manifold. The Roberts move by using Roberts O3 move, we can say the three manifolds are diffeomorphic, homeomorphic. But only O1 and O2 cannot, we cannot, only O1 and O2 don't change the right one to the left one, vice versa. We need all three. Only O1 and O2 cannot change the right one to the left one.
What is the coefficient of the other curve on the right?
Anything. Or in the solid torus, we cannot define the linking number. Or in general. Or in thickened surface, we can define the linking number. So in this case, arbitrary. And anyway, why we need all three? The reason is they represent the different four manifolds. The three manifolds are diffeomorphic, but four manifolds are different. The reason is four-dimensional two-handle kill this generator of the fundamental group, this loop. But pi 1 is Z. The fundamental group is Z. The fundamental group is not Z of four manifolds. Let F be a closed-oriented surface. Let M be a compact-oriented three-manifold with boundary, whose boundary is F and F, with the boundary condition B. Then we obtain a framed link in F cross the interval with the symplectic basis condition F, which represents M. Thus, we obtain a framed virtual link. Kaufman proved the following. Kaufman talked about it last week here. We define quantum invariants for framed virtual links. If framed virtual links L1 and L2 are changed into each other by Kirby moves, then each of the quantum invariants for L1 and that for L2 are equal, is equal. For now, we do not consider three manifolds for L1 or those for L2. We only consider framed virtual links, L1 and L2. Kirby moves mean the only O1 and O2 moves. Note, O1, O2, and O3 moves can be regarded naturally as operation on virtual links. Note that theorem 1.5 does not answer the following question. If framed virtual links are changed into each other by the O3 move, then are each of the quantum invariants for L1 and that for L2 equal? Is each. This Kaufman defined quantum invariant for framed virtual links. We want topological quantum invariants of three manifolds. We must answer or avoid answering this question in order to define a topological quantum invariant of compact-oriented three manifolds with boundary with the condition B. If a framed link L in thickened surface represents a simply connected four manifold V, we call L a framed link with a simple connectivity condition S. By Robert's result, we have the following. Let M be a connected compact-oriented three manifold with the boundary F and F with the boundary condition B. Then M is always described by a framed link in sequence surface with the symplectic basis condition F and with the simple connectivity condition S. This part is important. For example, both represent the same three manifold. The four manifold is not simply connected. The four manifold is simply connected. So we use this one, this type. An idea of the proof. We use all three moves twice. A part of a second surface, adding a framed link to the original one by the operation O3. Then four-dimensional two-handle kill generator of pi 1. Example, this three manifold is not simply connected. This three manifold is homeomorphic to this three manifold because of the O3 move. But four manifolds are simply connected. Four manifolds are not simply connected. This four manifold is simply connected. We use this type. We generalize the results of Kirby, Feng, Rook, and Roberts, and we prove the following. Let F be a connected cross-oriented surface. Let M be a connected oriented compact three-manifold with boundary F and F with the boundary condition B. Let L and L prime be framed links in F cross the interval with the symplectic basis condition F and with the simple connectivity condition S that represent M. Then L is made from L prime by a finite sequence of handle slide, adding and removing the wrist joint trivial knots with framing plus minus 1. That is Kirby moves. Note that under the hypothesis of this theorem, we only use Roberts moves O1 and O2. We managed to avoid the O3 move. Under these assumptions, we have four manifolds V and V prime as described in definition 1.6. Then V and S2 cross S2, S2 skew cross S2, CP2 is equal to V prime, S2 cross S2, some copies of S2 cross S2, some copies of S2 skew cross S2, CP2 is equal, different. Note, Kirby move, or I say again, Kirby moves means only O1 and O2. If we do not suppose the simple connectivity condition S, L is not made from L prime by a finite sequence of Kirby moves in general. Recall figure 1.8. It is the same as figure 1.8. Both the right one and the left one are not changed into each other by only O1 and O2. Because this four manifold is not simply connected. So the simple connectivity condition S in theorem 1.8 is important. If M is a three manifold, the boundary is F and F. L and L prime is in second surface. L and L prime represent M. If both satisfy condition S, they are changed into each other. They are changed into each other only O1 and O2.
There's supposed to be rock work and blasting around Port O, so there might be some delays. So I think it might have lost some time.
Idea outline of the proof. Second surface attaching two handles and we get M. This there is four manifold V. There is another four manifold V prime. This is M. Both are M, but four manifolds are different. Take a connected sum of V and a finite number of CP2 and CP2 bar. Call the result V again. Attach V and V prime by the identity map of M and F cross the second surface. Make a closed oriented four manifold V and V prime naturally. By using blow up and down, we can suppose the signature is 0. By the fourth cobordism group, there is a compact connected oriented five manifold double. V and V prime, consider the union of V and V prime. There is a five-dimensional manifold double by cobordism theorem. By handle decomposition theory in the Kirby's book, we can assume that double has a handle decomposition V cross I, V prime cross I, and five-dimensional two handles and three handles. Only two handles and three handles, V is changed into V prime. The outline of the proof. We can suppose that W has a handle decomposition below. First, W is connected, so first we remove 0 handle and 5 handles. 1, 2, 3, 4. Attach 6-dimensional 2 handles to W. Strictly speaking, regard W as second W and double cross 1. And kill all kill all 5-dimensional 1 and 4 handles. Here we have the following. Attach only two handles and 3 handles. V is changed into V prime. The boundary of V cross I and 5-dimensional 2 handles minus V. Call V again. The boundary of V prime cross I and the dual 5-dimensional 2 handles minus V prime V prime again. As a dual of three handles, the dual of five-dimensional three handle is five-dimensional two handles. Then V and V prime are diffeomorphic. One way of saying this is that the new V is obtained from the old V by a surgery by using five-dimensional two handles. It is very important that the old V is simply connected. Therefore, the new V is obtained from the old V by a surgery along the trivial one-dimensional link in 4-ball in V. Here is an outline of the proof. If a four-manifold V is simply connected, then the core of the attaching part of five-dimensional two-handle to V is a contractible circle in V. Kirby's textbook, page 59, line -8 to -7. Therefore, the new V is the old V and some copies of S2 cross S2 and some copies of S2 skewed cross S2. V prime the new V prime is the old V prime and some copies of S2 cross S2 and some copies of S2 tilde cross S2. Because the attaching part is trivial link.
Could you explain what S2 cross tilde S2 is?
Okay. Okay. Wait. S2 cross S2 tilde is sphere bundle over sphere and non-trivial. There are two sphere bundle over sphere, and one is the trivial one is S2 cross S2. The non-trivial one is S2 tilde cross S2, skew cross S2. It is diffeomorphic to CP2 and CP2 bar. It is explained in the Kirby's book.
Thank you.
You're welcome. In conclusion, we have the following. Assume that V and V prime satisfy the simple connectivity condition S. Or S. We change V and V prime like this, but they are simply connected again. Let V be represented by a framed virtual link L. V prime is represented by L prime. Then there is a framed virtual link A and A prime, which is a disjoint union of L. Some copies of trivial knot with framing ±1 blowing up down. Some copies of the hop link with 0, 0 or 0 ±1, S2 cross S2 and S2 skew cross S2 with the following properties. A satisfies the simple connectivity condition. There is a different map from the four manifold represented by A to A prime, which maps F cross the interval to F cross the interval with the fixed loops. By using surf theory as written in Robert's paper, we have that A and A prime are changed into each other by a sequence of handle sliding O2 moves.
Here, Susan?
Let F be a connected closed-oriented surface. Let M be a connected compact-oriented three manifold with the boundary F and F with the boundary condition B. Let L in F cross the interval with the symplectic basis condition F be a framed link with a simple connectivity condition S, which represents M. Regard L as a framed virtual link. Define our quantum invariance of M to be Dye-Kaufman quantum invariance of the framed virtual link. By theorem 1.8, we have the following. Main theorem, definition 1.9 is well defined. That is, each of the quantum invariants M is a topological invariant. We avoid O3 move. Under the condition S, under the simple connectivity condition, we don't need the O3 move. So we can say Dye-Kaufman quantum invariant becomes topological quantum invariant of today. Section 2. Quantum invariants of knots and links defined via virtual links. Let L be a two-component one link in the three sphere. The complement has the boundary torus and torus. A meridian and longitude pair is defined naturally. By using these pair, we can define our quantum invariant for the complement of the two-component link. By using meridian and longitude in both, we can define symplectic basis in both. So we can define our quantum invariant of the complement. Let K be a one knot in the three sphere. There are many natural ways to make a two-component one link from K. Split link made from K and the trivial knot. Split link made from K and the fixed knot, trefoil or figure 8 or and so on. Make a two-component split link made from K and K, or there are many ways. Make a two-component link made of K and the trivial knot T, so that K intersects the two disks which bound T one time geometrically. There are many natural ways to make a two-component one link from K. We can choose such a method to determine a two-component link associated with a given knot K. The complement of that two-component link L has the quantum invariants described herein. Call this call this two component link L. The make L from K in some ways. The complement of the two component L has the quantum invariance described herein. By using the complement of L, we can define our quantum invariance for K. In this way, our quantum invariance produce classical knot invariance and classical link invariance. Main theorem 2.1. Virtual links make new quantum invariants of classical knots and links in the 3-sphere, which are calculable and non-trivial, as explained above. We will show explicit calculation of some examples in Dai Kaufman Ogasa's paper in preparation. Heather Dai will talk about it here next week. Oh, anyway, I said, okay, yeah, that's all.
Thank you.
Thank you very much.
Yes.
Yeah. Sorry, I forgot to unmute myself. All right.
Is Heather scheduled for next week or a little farther on? I forgot.
I will look up the schedule and send it round. I can't recall it offhand at the moment, but thank you very much for your talk. And are there any questions?
Are the slides available somewhere?
Yeah,
Oh.
we will make the slides available if you could send us the slides for your talk, or perhaps I think it's the paper, probably, isn't it?
There's a paper, but I think you made some slides especially for this, didn't you, Eiji? Heather
Yes.
just wrote in the chat line that she thinks she's scheduled for after Thanksgiving. That's probably more comfortable for her.
Okay, well, maybe it is Dale next week then, but I will look up.
Yeah, I will put this file soon, and this talk is based on this paper.
Okay, well, thank you, Eiji. I guess it's quite early in the morning for you. Is that correct?
Yeah, yes, it's AM 2:48 now.
So it's heroic of you to give this talk now. So we are very grateful.
Thank you very much.
Yeah. Okay. So, okay. Well, if there are no more questions, I will end matters here. And I probably it's Dale next week, but I will check. Is that okay, Dale?
Yeah, that's fine. Either way.
Yeah. Okay. It's Thanksgiving, is it next week?
No, we've got
No,
a bit
following
of time.
week.
Oh, okay. Well, anyway, we'll sort something out, and I'll send around the details. So once again, thank you very much, Eiji.
Thank you.
Thank you.